Okay, so now we're going to work through a practice FRQ that deals with these topics of series and Taylor and Maclaurin polynomials, so you can kind of get a feel for what will definitely be one of your 6 questions on your APEX. So the first one, first of all, it says g is a function defined here. Now usually we like defining these term 0, 1, 2, 3, and then ... up to the general term, but sometimes they express it as a series in this nature and then give you a sample of what those initial terms would look like. So the first thing it wants us to do is use the ratio test to determine the interval of convergence of the Maclaurin series for G. So this is going way back to day 1 when we first talked about power series and finding those interval and radius of convergence using the ratio test. So let's go ahead and set it up. Now one thing I want you to be aware of here is when you're plugging in the n plus 1 term, remember this is what we're doing for the ratio test. When you're plugging in the n plus 1 into these spots here and here, you need to use parentheses. So the setup would look something like this. So just be careful with these two particularly. And then remember, we're really dividing it by the initial general term, but we're going to multiply by the reciprocal and save ourselves some paper. So that's going to look like 2n plus 3 over negative 1 to the n x to the 2n plus 1, all in absolute value. And then if you remember, one of the things we're allowed to do here is we really can just ignore the alternators because we're in this absolute value. Okay, and so we're going to end up with x to the 2n, and then this is really plus 2 plus 1, so plus 3. And I'm going to pull this term over here with it, and then 2n plus 3 over, again, 2n plus 2 plus 3, or 2n plus 5. If we remember our exponent rules, we know that with the powers of x, they can be separated. And then there's not too much we can do with the 2n plus 3 and 2n plus 5, but that's what the limit is going to address here in a moment. So this and this term will simplify away, and we'll be able to write it as the limit as n goes to infinity of x squared times 2n plus 3 over 2n plus 5. And thinking of our limit rules, we have the same degree on the top and bottom, so it's a ratio, and 2 over 2 is just 1. So this is just going to give us the absolute value of x squared must be, well, I guess I can use equals there, must be less than 1. And so that means that we're looking at a possibility of the interval being from negative 1 to 1. But we need to check those endpoints. That's our favorite part, I know. So let's check if x equals negative 1 and if x equals 1. Okay, so if x equals negative 1, we're looking at the series from 0 to infinity of negative 1 to the n times negative 1 to the 2n plus 1 all over 2n plus 3. Okay, so I'm going to rewrite that where all of the bases of negative 1 are combined. So that'd be negative 1 to the n plus 2n plus 1. So that's simply 3n plus 1 over 2n plus 3. Okay, now this is definitely going to stay odd because of the plus 1, and so this is in fact an alternator. It's not going to give us a positive or a negative every single time. And so what we're really looking at here is the alternating series. So this is an alternating series. So we're going to think about that test for convergence. Remember, we think of it as 1 over the function without the alternator. So the limit as n goes to infinity of 1 over 2n plus 3 passes our nth term test for convergence, and 1 over 2n plus 3 decreases, so converges. by AST. Okay, now we need to do the same thing for x equals positive 1. This one should be a little bit easier because we're going to have negative 1 to the n, and then this is going to be 1 to the 2n plus 1, which basically we don't really care about because it's just going to stay a 1. So really we're going to get something that looks very familiar. It's going to be another alternating series with the same exact result. So both of these actually have the same explanation, and thus both are included in our interval of convergence. So we would say that the radius of convergence is 1, and the interval of convergence is inclusive -1 to 1. Okay, part B says the Maclaurin series for G evaluated at x equals 1/2 is an alternating series whose terms decrease in absolute value to 0. The approximation for G of 1/2 using the first two, that seems important, first two non-zero terms is 17 over 120. Show that this approximation differs from the actual value of G of 1/2 by less than 1 over 200. So this is using that error alternating series error bound that we have discussed last unit. So if we're thinking of the fact that we want to show this approximation differs by less than a certain amount, it means we need to find the error of these first two non-zero terms. And basically, we've discussed that it means that this absolute value of this error has to be smaller than whatever the third term is. So to prove that it's more accurate than 1 over 200 in its approximation, we're going to find this third term and show that it is smaller than 1 over 200. And the way we're going to do that is to use the function that they've given us here. We can see that the third term is x to the 5th over 7. And just to clarify, because I know the counting the term thing can get confusing, technically this is term 0, 1, 2, but if they're talking about the first two non-zero terms, this would be the first and second non-zero term, so we're thinking of this as the third non-zero term. So I hope I didn't just confuse anyone. But basically, let's figure out, we know the third term is x to the 5th over 7, so then let's find it at x equals 1/2. That would be 1/2 to the 5th over 7. That's going to be 1 over 2 to the 5th, or 1 over 32, and I'm going to pull the divide by 7 out as time 1 over 7. And guess what? That's going to give us a beautiful number, 224, which is in fact less than the error they asked us to guarantee. So that's really all you're doing there, is knowing that, making the connection that you need to find the third term, and that you know that your error has to be less than that. So thus, if it's less than that third term, it's going to be within the error they're asking about, which is 1 over 200. Okay, and then for part C, this is actually pretty easy in comparison to the first two. It just wants the first three non-zero terms and the general term of the Maclaurin series for G prime. So they told us that the function we're looking at the top is G, so we're basically going to write this out and derive it. Okay, and we just go term by term, so this becomes a constant. We bring the 3 down, that becomes x squared, it's still all over 5. We bring the 5 down, x to the 4 all over 7. And just remember with the general term to leave n's alone, right? The only thing that we're really going, I know Stella, I hope they remember too. The only thing we're really going to be changing here is the one that has a base of x. So that means that yes, the expression 2n plus 1 comes down to multiply, and then 2n plus 1 minus 1 leaves us with a new power of 2n. Okay, but that's it. There's nothing else for us to do there with the other terms. So that's your answer.